You can read again, starting from the beginning. You can read and you can start from the beginning. If you hear me.
Surface property, different from the organic foulant. The bacteria can not only attach on the surface, but also can grow on the surface. Moreover, the dead bacteria also, as well as the cell matrix, become another type of organic foulant which cover on the surface. That will block the pore size. So it's important to reduce the foulant adsorption and also avoiding the bacterial growth to decrease the membrane falling. Actually, there are many types of the membrane falling modification strategies. Here, I won't introduce in detail, but then how to prepare the antibacterial and antifouling membranes. Actually, roughly, I divide in two types. One is using the same components, and another one is using the different components. For the first one, the silver nanoparticle or silver ions, graphene, also copper are always used. But for the second time, the researchers construct two functional layers, including use PG, beta CD, sweet ionic copolymers to prevent organic fouling, and using some drugs, copper and quaternary ammonia to reduce the biofouling. In our research, we tried to build a combination of quaternary ammonia and the sweetened copolymer for proved antibacterial and antifouling property of the membrane for sustainable application. One strategy is controlling the quaternary ammonia groups and the sweet ionic groups, controlling the composition to get the antifouling and antibacterial property. Another way is we're using the charged polymers to get the mixed charged polymers and to regulate to get the antibacterial and antifouling layer by regulating the charge and the composition. Here I will introduce 3 strategies we use to make the antibacterial and antifouling membranes. First one, we creating the inner quaternary and outer the ionic layer for improved performance. In this method, PVDF and the PMD membrane was prepared by the NIPS process. Then PMD is a kind of polymer that is containing the tertiary amine. Then the membrane is quaternized by the PCMS. Here, PCM not only we can quaternize get the quaternary amine, also we bring the double bonds onto the membrane surface. Then third steps, we're using the radical polymerization on the membrane surface. We bring the wet ionic monomers onto membrane surface. Then we can make that the inner surface is the quaternary amines and outer surface is the wet ionic copolymers. Here the characterizations for the FDIR, we can show that we can show from the 989 centimeter, we can find the quaternary groups by the second step. We also can find the from the 1044, we can get the we can confirm the sulfonic acid group from the third step. So from the FDIR, we can get that our preparation is succeed. And also from this figure, we can find that is a PCMS participate in the polymerization of the wet ionic monomers on the membrane, which can improve the surface stability. From the XPS, according to the wide scan and the core-level nitrogen signals, we confirm that the sulfur and also the quaternary ammonium group. We can, according to this result, we can calculate the graphing degree of SBMA was about 0.3 microgram per centimeter square. Then we calculate the surface charge. Actually, it becomes much more weak positive charge, and it becomes more hydrophilic because we introduced the wet ionic polymer, and also the surface pore size become reduced because of the surface grafting process. Most important, another we can find, although the pore size decrease, but the hydrophilicity increase. Actually, the final membrane, the water permeance of the final membrane increased. Then we using the protein static adsorption experiment. We found after our final membrane that we can get very low BSA adsorption, and we confirm our results also by the filtration experiment. Then we conduct the membrane in using some bacterial suspensions. One is in serous and another one equally. We can find that all the surface on our membrane with the wet ionic and the quaternary, they have the few the Q rate is over 97%. That means that our membrane have a very broad antibacterial behavior. And in this figure, we also found that after we soaking this membrane in the bacterial suspension for 2 days, after quaternary process, there are the many bacteria accumulated on the membrane surface. But on the surface with the wet ionic, we can find only few dead bacteria foreign attached on the final membrane. From the result, we can find that in the quaternary ammonia and outside the wet ionic polymer, lay on your membrane was succeeded constructed, and the membrane showed very excellent antibacterial and antifouling property. For stage 2, I introduced that in development of the membrane with well-dispersed polyampholic copolymer via a composite configuration process. Here we give the preparation process. That the composite configuration process means that our copolymer, we put the polyamphilytic copolymer in the configuration base, and we introduce. That means our polyamphilytic copolymer can introduce deep side of the matrix. It's very different from the traditional surface coating, and this the polyamphilytic copolymer can be well dispersed in the membrane matrix. We characterize the surface hydrophilicity to degrees even lower than by the coating method. We also we characterize the surface charge. For the original membrane, it's very negative, but for our membrane, we can the surface charge is very neutralized. For the water permeance, much higher for the original membrane, and also for the BS filtration, we can find that the flux retention or total recovery is much higher than the original membrane. In this research, we carefully studied the membrane matrix. We use the eye attention attached measurement. We use the organ to peel the surface surface in the matrix. Actually, we found some very interesting phenomena. By the membrane made by the configuration process, we can find even we use 1 to 5 times each, the membranes shows very similar compositions. But for the membrane made by the coating method, even after 1 time iteration, we find the surface composition changed well. That means the copolymer is just attached on the membrane surface by the coating. But if this of the polyamphilytic copolymer exists in the membrane matrix and dispersed well. So actually, our membrane that means our membrane have showed a very stable performance compared to the much more stable compared to the coating method. So we can get to the conclusion that the composite configuration process is expected to provide a novel fabrication method for modifying membrane to achieve very excellent permeability and antifouling property. It also expects to overcome the processability problem of the polyamphilytic. Let's move to this next. I will introduce the strategy 3. We're enhancing the antibacterial and antifouling property of the polymeric membrane using surface charge regulation. Here is the route 1. That means we have the route 2.
على الببليكيشنز هتلاقي الببليكيشنز بتاعتي افتح اي ببليكيشن وخد زي ما مكتوب. واضح؟
Okay. So I introduced the route 1. That is we grafted the positive charge monomer onto the negative charge surface via the UV radiation. The surface charge is regulated by controlling the substrate composition and the surface grafting conditions. We also characterize the water contact angle, and we found that the membrane become more hydrophilic. Then also we
يعني
found
مش
the
هي اللي تنزله.
we tested the
عملت
underwater oil contact angle. We found the membrane become super oliphobic, super oliphobic. Then also we tested the surface charge. Actually you can see also the surface charge is also neutralized. That means it has a high potential for antifouling actually. Then we also using the protein adsorption and also the bacterial adsorption. We can find after the surface grafting, the adsorption is very low, and we also try to find the bacteria on the membrane surface after attaching. We can find for the original membrane there's many bacteria soft on membrane, but there's always no dead bacteria on surface. But for our membrane, for our modified membrane, we can find there are few bacteria attached on the surface, but all the bacteria have been killed. That means our membrane have a very good antifouling and antibacterial property. And now we also use the membrane to do the filtration experiment. We can find for the BSA solution and the oil water emulsion, the water flux maintained very stable. But for the original membrane, the flux decreased sharply. Also, we found that if we use our membrane, we can get very high water flux retention. Here we have some explanation. Because of we introduce the MTAIC onto the membrane, the hydrophilic component further improves surface hydrophilicity. Meanwhile, MTAIC neutralizes the surface charge. In addition, a polyphotic copolymer was formed. Such a copolymer was recognized as an antifouling component. Therefore, a more hydrophilic and a non-charged surface containing polyamphiphotic copolymer was formed through a simple surface grafting method. Another reason that the low bacterial adhesion on the modified membrane was the antibacterial property of the ammonia groups on the MTAIC. This property effectively prevents bacterial growth after the surface adhesion. So here I also introduced the rule 2. We have the similar strategies, but we use the positive charged surface and the negative charged monode on the membrane. Actually, we can also get the very low protein adsorption and a very high bacterial killing rate. Here are the conclusions. From our research, we successfully make the membrane with an inner quaternary ammonia and outside sweet ionic copolymer layer. And also we make the membrane with a well-dispersed polyamphiphotic copolymer via a composite coagulation process. Then we can make the membrane antibacterial and antifouling property membrane by the surface charge regulation. Our membrane show very excellent antibacterial and antifouling property, which is a potential for complicated water treatment. Now we thank for the some fundings also Professor Zhu and Professor Matsuyama, and also we'll thank 2 students, Dr. Wang and Mr. Zhu, for their contribution. Thank you.
Thank you, Dr. Hang, for your presentation.